This is View Calculus. We're doing topic 3, the limit definition of the derivative, and this is video 3 in this series. So at the top, you'll see a reminder of what our limit definition of the derivative is. In example 3, we're given something that's cubic, and that's going to be not super fun unless you remember Pascal's triangle, so we're going to work on that a little bit. Okay, so the first thing I should do is I should write down what this is going to look like, right? So f prime of x is the limit as x approaches as h approaches 0, rather. Come on, brain. It's going to be long, so we're just going to go ahead and give myself some space. All right, so in red, I'm going to do f of x plus h. Anywhere I see an x, that means I'm plugging in the quantity x plus h. So for x plus h quantity cubed, which is the part that's going to take some work off to the side in a sec, minus a 2 times an x plus h plus a 1. That's this whole thing with an x plus h plugged in, minus, and in green I'll do f of x, this exact formula, but in parentheses after that minus sign because we're subtracting it, okay? Cool. All right, so that's my setup, right? This is my setup right here. My biggest task ahead is to simplify this x plus h quantity to the third. So up in the top corner here, I'm just going to remind you about what Pascal's triangle is. If you want to FOIL out x plus h quantity to the third, you could just do x plus h times x plus h, FOIL that out, and then times it again by x plus h, and that's fine, but it's not super duper awesome. There is a faster option, okay? The faster option is, when we FOIL out binomials, we can use a thing called Pascal's triangle, designed by Blaise Pascal. So Pascal's triangle, if you remember it all, has ones at the top, and then in each subsequent row, we put a 1 on the outside, and then sum the two terms above it to get the next term. So 1, 2, 1. The next row would be 1. The sum of 1 and 2 is 3. The sum of 1 and 2 is 3. And then a 1 on the end. So this is the row that we would want for something to the third, because this is row 0. This is row 0. This is row 1. This is row 2. The easy way to remember it is that if there's a 2 in the row, that's row 2. If there's a 3, it's row 3. So since this is an x plus h to the third, I'd want row 3. So essentially what happens is this thing would FOIL out to 1, 3, 3, and 1 as the coefficients, and then I would start with the x to the highest power, so x cubed, x squared, x to the first, no x at all, and in the back I do the same thing with the h, so h cubed, h squared, h to the first, no h at all, and this is what that FOILs out to. Now, you don't have to have that memorized, you can do it however you want, but man, is it helpful to know that, especially because if I'm doing this, I don't actually have to write this down anymore, I can comfortably do it in my head. Again, you don't have to know that, but boy, is it helpful. All right, so let's go back over here now. So this is going to be the limit as h approaches 0. So now, that thing I just FOILed out over here, I'm just going to have to put a 4 in front of all of it, right? So I'm going to get 4x cubed, right? And it was a 3x squared h, so now it's plus 12x squared h because the 4 times the 3, right? And then it was a 3xh squared, so that'll be a 12xh squared. And then it was just an h cubed, so that'll be a 4h cubed. So this whole thing is just this piece, minus the 2x minus the 2h plus a 1. That's that ugly, ugly red thing all cleaned up. And you can see that already took most of my entire movie screen. When I distribute the negative in front of the f of x, I'm going to get negative 4x cubed plus a 2x minus a 1. And all of that is on top of an h. So the hardest part of this problem was FOILing out that cubic. The reason I say that is at this moment, the same thing should happen that has happened in every other problem, which is any term that does not have an h will magically sum to 0. I see a positive 4x cubed. I'm not at all surprised when I see a negative 4x cubed farther down the line. These guys have h's, these guys have h's. I see a negative 2x. I'm not at all surprised when I see a positive 2x. This guy has an h. I see a plus 1, and oh hey, there's my minus 1. So it's not an accident that every term without an h goes away. It sums to 0. So if that doesn't happen, you should double check that you distributed properly because that should totally happen. So what ends up happening is that I end up with a 12x squared h plus a 12x h squared plus a 4h cubed minus a 2h all over h. Notice how all these terms now have a GCF of h. Sorry, there you go. So I'm going to yank out one of those h's, right? So I have the limit as h approaches 0. I pull out an h, and what's left is 12x squared plus 12xh plus 4h squared minus 2. Sorry, I got a little squeezed in there, but there we go. Okay, so now I cancel these h's, and I'm clear to plug in, and I get that my f prime of x is equal to 12x squared. Notice you're plugging in for h, not x. So 12x squared plus 0 minus 2. And my answer is just 12x squared minus 2. That's my f prime of x. Okay? Cool. Moving on, we're going to go ahead and talk about example 4. All right. Sorry, it's a lot of math. Okay. So example 4 is the first one we have with a square root, but it's arguably less math. It's just that people get uncomfortable sometimes with the square root. So in example 4, we have f of x equals the square root of x plus 1. Okay, so my f prime of x is going to be the limit as h approaches 0. So f of x plus h, which I'll do in red, is going to be the square root of x plus h plus 1, right? That's inside the square root, x plus h plus 1, because anywhere I saw an x, I was supposed to plug in an x plus h. And then in green, minus the square root of x plus 1. Now you might say, uh-oh, what do I do with this, right? How do I even simplify this? Well, this is one of those difference of squares patterns, right? This is my a minus b. I want to create a difference of squares. I want to rationalize by multiplying by a plus b. So that is going to be the root of x plus h plus 1 plus the root of x plus 1 all over that exact same thing on the bottom. X plus h plus 1 plus the root of x plus 1. Okay. So yet again, just like we saw the last time that we rationalized, I want to FOIL out the difference of squares floor, which is this top floor, a minus b times a plus b. I do not want to FOIL out the other floor. I want this h to cancel. So I'm going to get f prime of x equals, when I FOIL, so it's the limit as h approaches 0, the first terms, right, the root of h plus x plus 1 times the root of h plus x plus 1 is just going to give me an h plus x plus 1, or an x plus h plus 1, sorry. Outer and inner will be exactly the same terms, but with different signs. So they're going to cancel. That's the point of a difference of squares, right? So this is my a squared minus, and then my b squared is going to be root x plus 1 times root x plus 1, which is just going to be an x plus 1, right? And that's my b squared. On the bottom, I want to leave this h out in front because I really need him to cancel. So leave the h out in front times this whole quantity, the square root of x plus h plus 1, plus the square root of x plus 1, okay? So now, I'm going to clean up the top a little bit. When I do that, what I want you to notice, and I'm just going to clean up the top to the side a little bit here, it's an x plus h plus 1 minus an x minus a 1. Everybody that's not an h totally cancels, right? So I get f prime of x equals the limit as h approaches 0 of an h on top of h times that ugly bunch of root stuff, right? And when I do that, the h's cancel, and I get that I can plug in 1 on top of the square root of x plus 0 plus 1 plus the square root of x plus 1. So my answer ends up being 1 over a 2 root x plus 1. And that's my f prime. And I'll angle that up so you can see it a little better. That's my f prime of x. All right, so that's our example 4. We're going to do one last example. We'll do example 5. And as you can imagine, any example with a root is going to work the basic way this did. And the next one, in example 5, we're going to see an example with a fraction. And all of the examples that you have with a fraction are pretty much going to work the same way. So example 5, our f of x is 5 over x. So my f prime of x should be the limit as h approaches 0 of... So I'm going to have in red my f of x plus h. Well, that's going to be a 5 over an x plus h minus my f of x, which is a 5 over x. So again, we've seen this with common denominators before. I'm going to have to multiply this fraction by the denominator of the other fraction, right, and make it the thing over itself. And I'm going to have to multiply this fraction by the denominator of the other fraction. So what's going to end up happening is I'm going to get the limit as h approaches 0 of a 5x minus 5 times the quantity x plus h, which we'll deal with in a sec, all over an x times an x plus h, all over an h. And we're going to just leave that h chilling for now, because again, he's really not my problem until I clean stuff up, okay? So if I clean up the top, this becomes a minus 5x and a minus 5h. So I get the limit as h approaches 0 of 5x minus 5h, all over, and if you want to distribute the bottom, you can. You can also leave it as an x times an x plus h. It doesn't matter. All over an h, right? But that h is secretly an h over 1, right? Every fraction is actually over 1. So if we come back up to the top here, you'll notice that the 5x and the negative 5x are going to sum to 0. So I'm going to end up getting that this is the limit, as h approaches 0, of a negative 5h on top of, and again, I don't care if you want to make this an x times an x plus h, or if you want to make it an x squared plus an hx, it doesn't matter. This fraction divided by this h over 1. When we divide by a fraction, we multiply by the reciprocal. So this is negative 5h over x times x plus h times a 1 over h. Well, look what happens to that h. So I get that my limit as h approaches 0 is negative 5 on top of an x times an x plus h. Well, now when I plug in, I get that my f prime of x is a negative 5 on top of an x times an x plus 0, which is a negative 5 over an x squared, and that's my final answer. Okay, so again, not an easy thing to do. One of the good bits of information is that most of the time in calculus, once you get through this section, you're not going to be asked to do it over and over again, but it's good to know how to do it. So now you're going to try 5 practice problems that are similar to the 5 examples.